Perfect. Okay, so hi everyone, thanks for joining. My name is Svenja. I'm a PhD candidate in the Land Climate Dynamics group at ETH, and what I'm presenting today is joint work with Dominic, Lucas, and Sonja, who are also partly present, so they can help answer questions in the end. I want to talk about the global heat in 2023 and 24 in the sense that I think it's a typical black swan event. So that's a term that comes from finance, and it originates from the fact that during the Roman Empire, there was a saying that went, all swans are white, because in Europe, all swans are white. And it went so far that this became somewhat of a metaphor or a proverb for obvious truths, something you really don't have to explain until around, I think it was like 1700 or something. Some Dutch explorers went to Australia. They saw a black swan. They were shocked. And ever since, black swan events are events where something is able to shatter beliefs or convictions that people have held for a really long time, sometimes even centuries. And therefore, so it's rare, but it also has this high significance on how we think or what we think is possible or is not possible. So it's unexpected and it wasn't predictable, even though humans are humans. And sometimes in the end, they will try to, rationalize it in hindsight, even though it was actually impossible to predict before. So the event I want to talk about is the global heat in 2023 and 24. I think most of you have probably seen this graph in some variation or another. So we had, starting in July 2023, we had 12 months where every month was higher than 1.5 degrees above pre-industrial. Also, every month set a new record. And we had the highest temperature anomaly ever recorded in September 2023 at 1.8 degrees above pre-industrial. So the features of this event include that it was like really extreme, a lot of large margins by which records were broken, but it also lasted for a really long time and it was global. So that was already a lot, but then again, one thing to consider is maybe also that the time where the heat peaked, which was September, was at a time of the year where we usually have low variability values. And especially in this year, we had an ENSO that was, I think its beginning was recorded in July 2023, but usually its temperature impact is a bit lagged. So we would have expected it to kick in like much later, maybe in late winter or even early spring of, than 2024. So the unusual timing is for sure also something to consider. And yeah, as I said, it kind of fulfills the criteria of a black swan event in the fact that it was an outlier. It had a high significance in terms of how people think what's possible in a climate system or not. And it was impossible to predict, or maybe that's even the question, because so on the Lake of Zurich, but also in the world of swan metaphors, there's not only black swans, but gray swans. And gray swan events are events that are also rare in extremes, but they were actually possible to predict. They're just extremely unlikely. So in other words, the question we try to answer here is, was this global heat that we've seen something really impossible to predict? Or could and should we have expected it given the level of global warming we currently have? And linked to this, of course, is the question whether in the future we should expect similar or even more extreme events. So how we do this is somewhat, I would say it's a standard probabilistic attribution approach. So I use generalized extreme value distribution to fit temperature anomalies, and I let the location of this distribution shift with global mean surface temperature and an index for ENSO. So the implicit assumption here is that this, in addition to internal variability, are the factors that control temperature in a way. Uncertainties are estimated in a Bayesian way, and the event definition, so I mean the global, like the spatial scale in the sense that it's global is kind of clear, but as I said, so what's the time scale? Is it the year of 2023? Is it this 12-month record-breaking period? Is it a single month? Wasn't entirely clear to me in the beginning, and I didn't want to define it beforehand and then potentially miss out on something. So yeah, that's part of the work, to find out in which ways was it actually so unique. And for the data, we have 3 different kinds of temperature data sets. For process variables, I use ERA5 and then SIMP6 model simulations. I have to say at this point, I'm only going to show results from GISTEMP temperature dataset, but it doesn't matter actually. Like, I've done it for all 3 and it always looks the same. And that even extends to some methodological choices. So for example, the choice of the distribution now is a GV, but I also tested normal. I tested GPD, so Pareto distribution. I played around with some kind of block maxima where I only take every year out of 5 and stuff. But results are extremely robust, and it's not very sensitive to all those choices. So that makes things a bit easier for us. So now what actually happens if we apply this probabilistic attribution to the observations and fit a GV to the temperature anomalies? I show you here the results for September 23 because, spoiler, this was the month where probabilities were the lowest, and thus it's the most extreme that we've seen basically. So the top right plot is the absolute temperature anomaly, and the lower plot is the difference from September 22 to September 23. Histograms are all years until 23. Then we fit the distribution as I explained, and the red line is September in 2023. So the area under the curve would be the probability, but as you can see, there's no area under the curve because it's so far outside of everything that has ever happened before. And yeah, like that's also why probability values are literally 0. Even the confidence interval only goes to 10 to the -4 for the temperature jump. So in IPCC uncertainty language, we could say this was exceptionally unlikely for sure. Now, maybe someone could argue, okay, but that's observations. We only had 140 years of data. Maybe it was some kind of freak event that just has never happened before. So I also checked SIMP6 models. And here it's again results for September. I show so for every SIMP6 models, I took the 20 years before reaching the global warming level that we currently have or had in 23. And you can see that what happened is at the very, very end of the range of what models predict. So it's not clearly outside, but definitely not inside. So yeah, again, I repeated this for the 12-month period. I repeated it for every single month, and September just looks the most extreme. So we kind of found our time scale. And if we think about swan in the swan metaphor space, it's definitely a black swan event because it was impossible to predict before it happened. So what I did here now is, yeah, somewhat simple. I mean, it's non-parametric. There's no assumptions tied to it. It's just counting occurrences. But if I repeat this probabilistic attribution, as I did for the observations, I also only ever arrive at estimates of very, very close to 0. However, this changes a lot if you just go a few years into the future. So in this plot, on the y-axis, you have probabilities of occurrence. And in 2023, we are all at 0, as I explained before. But then if we only go, I don't know, 5 years into the future, we are at 28, we're already at 5%. And in 10 years from now, in 2035, basically every other September will be as extreme as the one that we've observed. So in a way, you could say we were like just ahead of schedule. And the reason for why this increase happens and also why it happened so fast could be two. So either it's just because we have additional energy in the system. I mean, I'm using the highest forcing scenario here. But it could also be that temperature variability increases under higher global warming levels. So I repeated the same thing, but this time for the temperature jumps. And yeah, as you can see, not much happened. So first of all, mind the y-axis, which has different values. So we're staying at 0. And also going into the future, we're still at 0. So, okay, the temperature jump seems to be robustly unexpected for the coming decades. That's also, yeah, as a side note, maybe that's good because it justifies this kind of assumption of constant scale that we have in the GeV fit. And I will focus in the rest of the presentation on the temperature jump now, because this one is the one that seems to be staying extreme and was not like maybe 1 or 2 years too early. So an idea that we had was thinking, okay, it's a global anomaly, but it comes from somewhere, right? So maybe there were some regions where it was more extreme and others where it was less extreme. So I repeated the analysis for regions, for very large regions. It's basically just tropical land and ocean and extratropical land and ocean. But what you can hopefully see is that, so already in the left plot, this bar plot, land masses contributed more than half to the temperature jump, even though they are only a third of the global surface area. But it makes sense in a way that also land has a higher variability. But even if you take then the likelihood estimates, so the top two plots on the right show land, and the probability values here are lower than for the ocean. So we can say that at the time scale that we look at, which is September 2023, land temperatures were more extreme, and we are still stuck with extremely low probability values. So given that I kind of say this was impossible, but it still happened, it would be nice to understand how it happened or what exactly happened. So we tried to analyze which processes were important to build up the heat. And we did this by setting up like a very simple linear model. So it's a regression on grid cell level, where I take short-term fluctuations in total column water vapor, downwelling shortwave, radiation, and soil moisture, and try to predict temperature deviations. So the rationale behind this is kind of that water vapor, or like it's very closely linked to long wave forcing, together with short wave forcing, kind of decide how much energy we have available at the surface. And then soil moisture influences local temperatures via the energy partitioning. So yeah, it's a very simple model, but we just wanted to try and see how it works. So in this plot on the left, you see the observed temperature anomaly in era 5. In the middle, it's everything that we explain with this simple model as what I just explained above. And then on the right is the difference between the two. So the pattern that this model predicts is really similar to the observations. And also, in the difference between the two, you can kind of see some remnant El Niño warming, which is to be expected because I didn't include SSTs. But in general, it works quite well, surprisingly well, given how simple it is. And I only used 40 years of training, so to say. So what this means actually is that at least the relation between those drivers that we listed above and temperature hasn't changed much from the years before to 2023. And it's nice because now we can check which driver contributed how much. So in the lower row, contributions of water vapor, downwelling shortwave radiation, and soil moisture to the temperature anomaly. It's mostly water vapor and some shortwelling, shortwave forcing, downwelling shortwave. Soil moisture does not seem to be that important here. And in the next plot, I basically just now I summarized it over the 4 regions that I defined before, plus global. So you can see in every region, it's a lot of long wave forcing, and water vapor levels in the atmosphere were very important to build up this global heat. So of course, there's some cyclicity in there. So warmer atmosphere can also hold more water vapor, and then we have more downwelling radiation. That's why I also checked this time series here. So we see water vapor and shortwave forcing, and you can see that basically starting in 2023, really early, we had shortwave increasing a lot, and the water vapor levels kind of followed. So yeah, everything I want to say here is that basically shortwave preceded, and it probably enabled the high water vapor levels. But then for September, those were the ones that really led to this heat, I don't know, crashing all the records. And yeah, it's of course always the interplay between the two that you need. So in September 23, both were high, but long wave was really, really important. Okay, so this was all based on ERA 5. I did the same for the few comparable jumps in the models that I found, which, as you will see, are actually not that many. So no need to look at the plots in detail. My main point is here that there's a lot of long wave forcing going on everywhere. In each case where we had a strong temperature jump that was as high as the one we saw between 22 and 23 in September. So long wave forcing seems to be important also for CMIP6 models. And then we had this idea that maybe the ability of a model to simulate a jump, because as you can see, not all of them do it, might be connected to the sensitivity, water vapor sensitivity of each model. So, and in this case, I basically define sensitivity as the coefficient I get in this linear regression between water vapor and temperature. So here we have a lot of CMIP6 models. I put them into two groups. So this lighter blue color are the ones that tend to have higher temperature jumps, and the darker ones are the ones that tend to have lower temperature jumps. I was hoping for some kind of, difference in there. But yeah, honestly, no. Even if you want to see anything, you really don't see anything. But there's one more factor to it, right? So it's not only the sensitivity, but also the variability. So I also checked this, and here I would argue that you can see a difference. So models who simulate higher temperature jumps on average also tend to have a higher variability in total column water vapor. So that it seems to be very important, like for the models to be able to accumulate such large amounts of water vapor in the atmosphere if you want to reach high temperature jumps. Of course, it would also be interesting to see where reality lies or where reanalysis lies within the spectrum. So here we compare CMIP6 models on the left with ERA 5 water vapor sensitivity, and it's kind of at the upper end of the spectrum, I would say. If you check the variability, it's really in line with the model range. That was a bit different from what I expected. So if you only look at the models, it seems to be the sensitivity that kind of governs if you have high temperature jumps or not. But if you compare it for ERA 5, the sensitivity was actually kind of important. So, right, that already leads me to some preliminary conclusions based on the plots that I showed you and the analysis that we've done. So, for sure, we can say that September 2023 was exceptionally unlikely, and that's consistent in climate models and in observations. Then, in particular, the temperature jump is interesting because it remains unlikely even under higher global warming levels. The land temperatures were more extreme than the ones over the ocean. And that ties into the fact that long wave forcing and record high water vapor levels were important, of course, in interplay with short wave forcing. And that's also something that we see in the model. So the ones that accumulate large amounts of water vapor in the atmosphere are more likely to simulate high temperature jumps. Okay, we are on the way to being done, but not quite yet, because there's one more question that we should address. And that's the reason for why, one of the reasons maybe for why 2023 has been so widely discussed. And it also links to this like high significance aspect of black swan events. And the question is whether 2023 hints at an accelerated warming rate. So recently there have been some discussions, for example, in this paper by Hans and others in 2023, where they claim that the climate sensitivity might be actually higher than we previously estimated, and that the Earth energy imbalance is increasing faster in the last 1 or 2 decades, and that we thus should be extremely careful with emitting even more greenhouse gases into the atmosphere, because the warming that they cause could be higher than what we think. So there has been a lot of thought on whether this extreme global global warming is a proof or at least some kind of sign that we are actually in somewhat of a new regime of accelerated warming. And the answer to the question depends on what kind of drivers you think are responsible. So on the list of suspects, there are, of course, greenhouse gases, but now also in connection with the climate sensitivity. Then there's internal variability and ENSO. We had some new shipping regulations, which led to sulfur aerosols decrease much faster in their concentration than we, for example, prescribed in the models. There were some volcanic eruptions, which increased the stratospheric water vapor levels and thus had a positive climate impact, other than most volcanic eruptions who are rather cooling. There was a new study that came out where they claim that the global albedo has been lowered, mostly because of a lowered low cloud cover, and that would increase shortwave energy input basically, and thus also accelerate warming. We are currently at a maximum of the solar cycle, and it's a strong maximum. And of course, there could also be another driver, possibly also in combination with one of the ones that I've listed here. So depending on which of the drivers you think are important, your answer at whether 2023 hints at an accelerated warming is no. I would say if it's mostly targeting interannual variability, it could be maybe if it's something like reduced low cloud cover, also greenhouse gas emissions, and the increased climate sensitivity, where you don't know really where it comes from, or there's like some internal feedbacks going on that we haven't quite captured. And also into this question, and also with other studies that have come out. So of all those factors that are listed here, which ones are actually represented in a statistical model? There are those. So we have the covariates, greenhouse gases, and GMST. We have ENSO, and we also should have the solar cycle in there. What we do not have are the new shipping regulations and volcanic eruptions with positive climate impact. And what we also do not have, but what is also really uncertain, is the reduced low cloud cover, and of course some other driver that we don't know about. So one could say that in this statistical model, we primarily have greenhouse gases and internal variability. So, and we reach very low probability values. So what could be the reasons for this? So I would say either it's just an exceptional case of internal variability. I mean, we have seen that some models also show comparable temperature jumps, although maybe I would have expected to find it a bit more often in the thousands of years of runs that we have, but okay. Then it could be that climate models underestimate internal variability, but that's generally not the case. I mean, I've checked it, also other people have checked it. It could be that an external factor is missing, or it could be a combination of the above. And for now, I mean, if we go back to the conclusions, we have to, or I would say we started with a model that primarily focuses on internal variability, and we end up at least considering an external driver, and that would just not be contained in the statistical model. So according to our present knowledge, some climate models simulate the temperature jump, but only very few. It's possible that some kind of external forcing contributed to the heat, but that was not really the focus of the study. Nevertheless, to answer my question from the beginning, like, is this jump going to happen again in the future or not? I don't know. I personally, I would be really surprised if it happens in the like near midterm future. But yeah, let's see. I think we will all hopefully witness. So for now, thank you for listening. That was it from my side, and yeah, I'm open for questions.
Thank you. Please raise your hand or unlock your mic. And I think Melinda has a question already.
Yes. Yes. Hi. Thank you for the nice presentation. It's a really needed and interesting study. I am a bit skeptical about the statistical model you use. Maybe I also misunderstood things, or maybe because you didn't go into detail. But if you apply a GV to distribution of extreme events, you assume that your extreme events are identically distributed. So if you have a black swan, then that is an event which comes from a different distribution. So that is an event which you cannot find in your normal distribution, typical distribution of extremes. So I'm a bit confused about this applying GV or GPD to study a black swan, because I don't think that's possible.
Okay, yeah. I mean, so initially it wasn't clear if it's a black swan or not, right? Like you see something happening, it was really warm, but we also know that climate change is in full swing by now. So the first question was if it's even a black swan. And yes, if of course, if it's something different that we've never experienced, and if there's something else at play and it's just a different distribution, we can't say much about it. On the other hand, yeah, that would just like, there should be a plausible candidate, or we should just look into it. But as long as we don't know things, I think we have to start with what we know. And also, some of those external drivers should have been contained in the years before, not all of them, but some of them. So just stating that with everything we've seen until now, this was so unlikely, then at least hints at, okay, something must have changed. But yeah, I mean, of course, if it's something we don't know, we don't know.
Yeah. No, my point is just that if it is really a black swan, which you cannot predict, then you cannot trust probabilities which you obtain based on a GV or GPD. That's what I want.
Yeah.
Yeah. Okay. Yeah, thanks.
Please go ahead, Eric.
Yes, Svenja, very nice project, excellent and really very interesting. I particularly like the way you break down the heat anomaly in land and extratropical land. I haven't seen this. It is really a new aspect. A lot of people have been always talking about the ocean, so it's really cool. One thing that I'm not sure I fully understood, you've been saying that water vapor can also follow temperature, right? You've been sort of highlighting this a little bit, and a bit. I wasn't quite sure if I understood correctly how you disentangle cause and effect in this respect. I mean, how can you exclude that water vapor and actually even long wave is simply the consequence of a warm atmosphere, because a long wave downward also increases if you have a warmer and a more humid atmosphere. I think I don't think this is. I actually trust what you suggest is plausible, but I find it hard to disentangle it properly.
No, I mean, I wouldn't say actually, like I don't think it's possible to get rid of the cyclicity. Yes, a warmer atmosphere holds more water vapor, and that's it. I think my argument in here was more that in the end, for September, it was the water vapor that caused the temperature. So kind of no matter how it got there or why it got there, this was the forcing. But by seeing that, for example, in the months before we had some strong shortwave forcing, to me it looks like, there's some, okay, we had shortwave forcing, temperature rise, and then that was why we could have more water vapor in the atmosphere and then more longwave forcing. So I'm actually like, if there was a way to get rid of this, I would be extremely intrigued.
Okay, I don't know the solution. I just know that I came across the same problem before, and I found it very hard. But yes, okay. Thanks for the clarification.
Any other question? Please don't be shy. We have time.
I think there was something in the chat. Wait, let me check. Okay, yeah, no, enjoy your lunch.
Pascal, yes, go ahead.
Yes, hello, thank you for your presentation. So you mentioned Bayesian estimates of GeV at the beginning of your presentation. Can you elaborate quickly or briefly on this? Are you referring to the work that people like in Toulouse or other places did, or is it something on your own?
So I didn't do this. What I meant was just that the parameters of the GV and especially then also the uncertainty is estimated with the Markov chain Monte Carlo, and this is work by Matthias Hauser, who's also in our group, and I just adapted his code.
Okay, I see. So because there are so some people like Johan Robin and Aurélien Rib at Météo France devised methods that take into account well, they use models, but they take into account observations. But they do this locally. Here, it's obviously global, but I was wondering if you had used this type of approach, but it's slightly different. Okay.
Yeah, it's different in the way that I mean, what I do, it even works if you have no model data, right? You can only take observations or only take models, but there's no constraint, so to say.
And out of curiosity, so you do GEV fit, but on fairly long term and law and spatial averages. So what is the value of the parameters that you obtain?
Like the location parameter and stuff.
Like
You don't know.
the shape parameter.
I don't
Just
know.
is it a large negative value, a
No,
zero?
no, no.
You don't know. Okay.
No, it's not large negative, but I also don't know the exact values. But if you're interested, I can check it and let you know.
Okay. Thank you.
There any other question? Even in the chat, I've checked, but nothing so far. I don't know, is you want to add something maybe, Svenja, or?
No, if no one has questions, I'm also happy to, let you go. Oh, there's something. Yeah, okay. He has to leave.
Yes, thank you, Aaron. Bye-bye.
I would like to add something.
Go ahead.
Yeah, so just going back to Melinda's question. I mean, I'm sure you're aware, but we know that it's difficult to work with statistical models in this context. And that's also why Svenja did a lot of work just looking at what the models do without trying to statistically model it, and it doesn't really change the picture. I just wanted to point that out.
Yeah, I'm aware of the difficulties, I think. It's just that I think it's good to be aware of that there is somehow a contradiction, like black swan and fitting a GV distribution or any other distribution. So maybe it's good to be aware of that for like how you interpret the results and so on.
Yeah, I might add also a comment on this. So I think, but I guess the black swan picture was more something that Svenja wanted to mention, to say basically from what the statistics tell us, it seems to be an extremely unlikely event, or with a probability that could be close to zero, but on the other hand, you could still say maybe a very small probability of happening. And as Dominic has said, Svenja spent a lot of time also using different distributions, so GV, but also others, block maxima and so on, and the results always come out more or less the same. But actually, I must say, for me, I take the black swan analogy more as an illustration, as a concept. But I wonder, because you said, I mean, would you have specific methods to investigate a black swan event? Actually, I'm curious. This would be a question.
No, actually, because the nature of black swan events, I just read the original book of Taleb, so now I am really in the topic.
Yeah.
So the nature of black swan events is that you cannot predict them, because it
Exactly,
is
yeah.
usual is like I don't know, like COVID, or maybe, yeah,
I
like
think
COVID,
was
let's say
actually
COVID,
predictable.
if we consider the history, or 9/11, something which you cannot predict before, and it happens once. And then the gray swans are then events which you could predict, but then still it's hard to predict them, and they are related to fat tail distributions. So these are all things to check. But I think that the nature of the black swan is that that you cannot predict them, basically. So whenever then you estimate the probabilities, I think you should be aware that you are always underestimating the probabilities or return periods.
Yeah, I mean,
I don't think that we have the methods to predict black swans because of their nature.
Yeah, for me, at first, part of the work was even to find out if we get any kind of probability or not. Like, is it black or gray, basically? Maybe I took the answer away a bit too early, but like, just from knowing that we already have a lot of climate change going on, could also have been that this is something within the range of possibilities that we have, and it could have been predicted even if probabilities are low. But it turns out to be not really the case.
Yeah, and Svenja, maybe I'm not sure if you mentioned this at the end, but we can say maybe this one event was a black swan with very extremely, but it was in any case an event with very low probability of happening, but still there is a small probability that it would have happened. But the thing that we would not expect to happen is for such an event, a second such event with such a big jump to happen, and this would be something that would be totally outside predictability.
Okay, should we close, Manon?
Yes, thank you very much.